This video is the first video in a series of videos that I intend to make giving a basic introduction to some of the works and results of the ancient Greek geometer Apollonius of Perga from his work Treatise on Conic sections. The Treatise on Conic sections develops some basic and quite advanced theory at the same time, involving circles, ellipses, parabolae and hyperbolae, the so-called conic sections. This particular video is going to concentrate mostly on some of the background theory, some of the historical side of things, also giving some basic terminology and definitions, with the rest of the videos concentrating on the work itself. A Treatise on Conic sections is amongst one of my favourite works from classical geometry, due to the way Apollonius uses really quite simple techniques involving proportions and ratio, congruences, similarity, and really manages to stretch them to their limit to wring out as much as possible from them. And in this way he really does manage to derive some really quite intricate and deep results regarding conic sections. Apollonius' Conics is a series of originally 8 books dealing with the properties of parabolas, ellipses, circles and hyperbolae. Of the original 8 books, only 7 have survived to the present day, although the 8th book is known to have existed at some point due to references to it from other sources. The first 4 books concentrate on what would be considered the more kind of fundamental properties of conic sections. The results from the first 4 books are considered to be maybe a collation of results from Apollonius's predecessors. He's collated these results, maybe refined them, presented them in a new style, but ultimately there's nothing overwhelmingly new about the first 4 books. But the first 4 books are necessary to go on to the next few books, so particularly the 5th, 6th, 7th books, and presumably the 8th book when it still existed. These develop the original results, so the work that is considered Apollonius's original contribution to the theory of conics. When I say that that the results are basic in the first 4 books and fundamental, I mean that quite loosely. Some of the results are, in and of themselves, are quite complicated to a certain extent, although not as complicated as some of the later results, obviously. Apollonius's work is considered to be of quite important, quite historically significant, and obviously it's not as well known as such as Euclid's Elements being probably the most well known work of classical geometry. But to read Apollonius's Conics is to really get an understanding of why it's right for this work to be considered as significant as it is. It really is a remarkable work with some really interesting results, and Apollonius is a virtuoso really when it comes to the application of the techniques that he's used to get these results. His techniques rely mostly on things like ratio and proportion, similarity, congruence, and a technique that's not very well known now, which is application of areas. But through these, Apollonius manages to get some really deep and non-obvious results about conic sections. For a modern mathematician, it can be quite difficult to follow sometimes Apollonius's work due to the difference in approaches. So for a modern mathematician, geometry is done usually via coordinate geometry. So a lot of it's reduced to kind of an algebraic form. So modern mathematicians are kind of conditioned to interpret algebraic results and work algebraically. Whereas in Apollonius's work, things are presented in a purely geometrical form. So in terms of areas, ratios and proportions, and it can be a little bit difficult to adjust to that that difference. So sometimes there are results to propositions that for a modern mathematician it can be quite difficult to interpret. For the ancient Greeks, particularly Apollonius, they probably have been quite natural, just like it's very natural for us to now to interpret algebraic results. But it just takes a little bit of time to adjust. So going at Apollonius's work with a strictly coordinate geometry head on your shoulders and stubbornly sticking to that kind of mindset is probably going to lead to quite a bit of frustration, because sometimes Apollonius takes quite a while to build up to a particular result using the techniques that he had available to him, that from a coordinate geometry perspective will seem quite obvious or trivial. And in that respect, the book can seem to go quite slowly. On the other hand, sometimes the book can seem to go very quickly, because some things are much easier to do in a purely geometrical environment than in a coordinate geometry environment. Sometimes coordinate geometry can have a tendency to overcomplicate some things because of the algebra that becomes involved. So sometimes it can feel that Apollonius is kind of glossing over some things a bit too quickly. So to read Apollonius means that you've got to adjust as well to the different pace, so it won't flow in quite the same way that you might expect from a more modern kind of textbook on geometry, for example. So it is worth spending a bit of time adjusting to that. Whether I recommend Apollonius's Conics to anybody really depends on what they want to get out of it. So if you expect to read Apollonius's Conics with the intention of becoming a better modern mathematician, then it's quite unlikely. The techniques that Apollonius uses are quite archaic. It's very unlikely that you're ever going to need to use application of areas. Ratio and proportion are used, but not to the extent that they are in Apollonius's work. So if you're wanting to become a better modern mathematician or geometer, then it would be much better for you to get a more modern kind of work to read, a more modern textbook. On the other hand, if you are genuinely interested in the historical development of the subject, particularly of geometry, and you are genuinely interested in how things used to be done, then Apollonius's Conics could be worth reading for you. But like I say, it might take a little bit of time to adjust, but if you are interested in that kind of thing, it is definitely worth the hassle. There are various versions and translations available of Apollonius's Conics, both in English and in other languages. There are pros and cons to using a particular version. No version is perfect. The version that I'm going to be referring to is the Thomas Heath version. So this was first published in 1896, so some 120 or so years ago. And some of the pros to use in this book are that I was talking earlier about the difference really between how things are done now in geometry and how things used to be done. Well, Heath tries to kind of bridge that gap a little bit. So he tries to retain some of the presentational style, original presentational style of Apollonius, while modernizing some parts. So bringing in some kind of algebraic derivations and translating some of the ideas, the geometrical ideas, into algebra, while still maintaining that geometrical feel to the work. There are some other pros to using this particular version, namely that even though it was written over 100 years ago, the notation is perfectly familiar to anybody that's got any kind of familiarity with modern mathematical notation. There's no surprises there. It's perfectly understandable. So even though if you don't necessarily understand the results and the techniques that are involved, you still kind of feel at home with the notation. Another upside to using Heath's version is that some of the, I think what he considers dead wood has been kind of removed, it's been taken out. So it does mean that it's a much more succinct version of Apollonius. So I have seen some of the other versions. Another version in particular I want to mention is a version that's available only on the internet, evidently, which is Boris Rosenfeld's translation, which sticks much more faithfully to the original presentational style of Apollonius. And if you look at that, it's a much longer work, much more detailed in some respects. And the reason for this is mainly due to the techniques that are available to us now that weren't available to geometers in ancient Greek times. So whereas some things Apollonius would have necessarily had to view as separate cases, from a modern perspective we can see these separate cases actually as capable of being rolled into a single case. So whereas separate propositions in Apollonius's time, there might be 6 separate propositions all proved separately, now we can just kind of roll them all into a single proposition. And that's what Heath does in his book. The downsides to using Heath's book are that sometimes it can feel that you're not getting the genuine Apollonius experience, because the style has been changed quite dramatically. You feel that you're not quite getting that genuine feel of how geometry was done. And this is where Boris Rosenfeld's translation comes in. You can get a much more genuine experience from reading something like that, but it is much harder work. And I'm going to give an example of that right now, just the difference in presentational style, just of the statements of the propositions themselves. So I'm going to give first of all an example from Heath's book. So the example I'm going to give it's just the statement of proposition 15 from book 1. There is some terminology there that I've not gone through yet, I've not defined. Don't worry about that just yet. I will be going through that later in the video. It's more just the contrasting styles that I'm wanting to focus on at this stage. So in Heath's book, this is proposition 15 from book 1, and this is Heath's translation. So, if through C the middle point of the diameter PP primed of an ellipse, a double ordinate DCD primed be drawn to PP primed, DCD primed will bisect all chords parallel to PP primed and will therefore be a diameter the ordinates of which are parallel to PP primed. In other words, if the diameter bisects all chords parallel to a second diameter, the second diameter will bisect all chords parallel to the first. Also, the parameter of the ordinates to DCD primed will be a third proportional to DD primed PP primed. So it's quite short. It's no longer than what you would expect in a modern textbook on geometry. And now I'm going to give the translation as it's found in Rosenfeld's work. Like I say, Rosenfeld's version is freely available on the internet. I would have been willing to pay, because the time that it must have taken to actually translate the whole work must have been immense, and I would have been willing to pay for it, but it is freely available on the internet. So here we go, it's the same proposition, it's the presentational style that I'm wanting to contrast here. So here we go. If in an ellipse a straight line drawn as an ordinate from the midpoint of the diameter is continued both ways to the section, and if it is contrived that as the continued straight line is to the diameter, so the diameter is to some straight line, then any straight line which is drawn parallel to the diameter from the section to the continued straight line will be equal in square to the plane which is applied to this third proportional, which has as breadth the continued straight line from the section to the point where the straight line drawn parallel to the diameter cuts it off, but such that this plane is decreased by a figure similar to the rectangular plane under the continued straight line, to which the straight lines are drawn in the latus rectum, that is the third proportional, And if the straight line drawn parallel to the diameter is further continued to the other side of the section, this drawn straight line will be bisected by the continued straight line to which it has been drawn. So there's a clear contrast there in the way in which the propositions are actually presented. And when you read Heath's version, sometimes you can be quite grateful for that, because I personally don't understand on a first reading what the proposition is actually saying when it's in a style that's much more faithful to Apollonius. But if you want that genuine experience, then maybe Rosenfeld's version, or maybe one of the other versions, would be much more suitable to you. So now we come to how are conic sections actually obtained. Well, typically conic sections, so circles, ellipses, hyperbolae, parabolae, are obtained from double cones, the surfaces of so-called double cones. If you look in modern treatments of conic sections, then probably they will typically be dealt with more in algebraic terms. So if you're dealing with a parabola, you might look at something like y equals x squared, or its whatever its parametric form is. Or if you're dealing with an ellipse, it might be x squared over a squared plus y squared over b squared equals 1. But if they are considered in more geometric terms, then they will be thought of as obtaining really from right cones, or cones of revolution. So what do I mean by that? Well, let's start with a circle. And this is called the base circle. And here's the center of the circle. I'm going to take any point now directly above the center of the base circle. So let's say that's here somewhere. Okay, and now I'm going to draw a line from this vertex to the circumference of the base circle, and extend it indefinitely in either direction. And then what I'm going to do is I'm going to rotate that line, keep this point fixed, rotate the line around that base circle, and what gets traced out by that line is the surface of the double cone from which the conic sections are going to be cut. So we get something that looks like that, and now I can start to cut my conic sections. And typically cutting parallel to the base circle will give me another circle. Cutting on kind of an angle, kind of a shallow angle, will give me an ellipse. Cutting with a plane parallel to one of the sides of the cone will give me a parabola, and if I cut straight down, then I'll get a hyperbola. I can cut other angles as well, but all of the sections that I get will be one of those four. However, as you read Apollonius's work, you will notice that Apollonius doesn't just deal with right cones. He deals with oblique cones. So an oblique cone is any cone that is not a right cone. So how are these obtained? Well, if we start with a base circle again, and this time we take again a point that's off that base circle, but it doesn't have to be directly above the center, it could be anywhere. So let's put it over here somewhere, and in the same way as we did with the right cone, we're going to draw a line from that point to the circumference of the circle. So I'll try and get it straight. So again, it can be extended indefinitely in either direction. And we do the same thing. We let that line rotate around. We keep this point fixed and rotate the line around the base circle, the circumference of the base circle. And what gets traced out is the surface of our cone from which we're going to cut the conic section. So we get something that looks like this. Okay, so as you can see, an oblique cone is a much greater generalization of the right cone. Now, this would have been considered, this is considered as one of Apollonius's most important kind of innovations, really, to the theory of conic sections. Before Apollonius, his predecessors such as Archimedes would have used right cones. They wouldn't have considered oblique cones. At least reading through their works, they don't consider oblique cones, they only consider right cones. But Apollonius decides, no, we're going to go for a greater generalization, presumably with the idea that with this greater, with this more general type of cone, we might actually end up producing a greater variety of conic sections. So maybe there are some conic sections that we can get from these oblique cones that we can't get from the right cones, and we want to study them. As it turns out, just to spoil the fun, every conic section that we can obtain from an oblique cone, we can actually obtain from a right cone as well. So it could be argued that this was an unnecessary overcomplication of the situation, but obviously at the introduction of this, that wouldn't have been known. If it turns out that every conic that can be obtained from these can be obtained from these also, that needs to be shown, and Apollonius does show that in his work, and I'll be going through that in a later video. So we can start cutting our conic sections from this, and if you go back to the modern kind of treatments of conic sections, we're back to these, by the way, to right cones, presumably for the reason that these don't generate any additional sections, and it might be considered as an unnecessary overcomplication. So in modern treatments on conic sections, we're back to these. But mostly in Apollonius's work, we're going to be dealing with these oblique cones. So we're going to, whenever we talk about a conic section as being obtained from a cone, the assumption will be it's come from one of these. At this stage, I feel it's necessary for me to just go through a little bit of terminology, introduce a few definitions relevant to Apollonius's work. So in the next couple of videos, I want to concentrate really on the main body of the work. So I want to try and get as many definitions out of the way as I can now. The first definition that I want to introduce is that of the axis of the cone. So using our diagrams from before, what I'm going to do is I'm going to draw a line from the vertex of the cone to the center of the base circle. And such a line is called the axis of the cone. Obviously it can be extended, it should be straight, but and I've already got it drawn in here from before, and once I've got the axis defined, then I can start talking about what are called axial triangles. So an axial triangle is formed from a plane which cuts the cone, a plane which contains that axis that cuts the cone, and the intersection of that cutting plane with the surface of the cone itself will produce what's called an axial triangle. So I'll get something that looks like this. The line here is the base of the axial triangle, and it will be a diameter of the base circle. And similarly over on the right cone, it would be like that. And I just want to draw some attention to some characteristics of these axial triangles, namely that with the right cone, an axial triangle will always be perpendicular to that base circle. But in the case of the oblique cone, that's not necessarily the case. I might have an axial triangle that's kind of tilted over to one side, so it's not necessarily perpendicular. Having said that, even in the case of the oblique cone, there is always it is always possible to cut at a particular angle with a particular plane that produces an axial triangle that is actually perpendicular to the base. So that's the axis of the cone and the axial triangle defined. At this stage I just want to define what is meant by a chord. A chord is a line that joins any two points on our section. So compare this with, for example, a chord of a circle. A chord of a circle joins any 2 points on the circumference of a circle. Well, we can generalize that idea to any conic section. So in the diagram that I've drawn here, this is our section. It could represent any section, so even though it looks like a parabola, maybe hyperbola, it could be an ellipse. And each of these red lines are chords. They're joining 2 points on the section. I've drawn them parallel for a specific reason which will become clear in a second, but in general these chords could join these 2 points, or these 2 points, or these 2 points. It really wouldn't make any difference. But once we've got the idea of a chord, then we can start to talk about a diameter. We can introduce the notion of a diameter. A diameter is any line that bisects a series of parallel chords. So that's the reason that I've drawn these chords parallel to one another. The line PM here, as you can see, it roughly bisects these chords. So the chord QQ primed is bisected at the point V being on the actual diameter. Obviously there would be an infinite number of these chords that extend in this direction. Obviously they'd be in between the chords that I've drawn, but PM is a diameter. And you might notice that the angle between the chords and the diameter is not necessarily 90 degrees. It's quite clearly not in this case, and diameters don't have to bisect their chords, this family of chords, at 90 degrees, at right angles. However, if we've got a diameter that does bisect a family of family of parallel chords at 90 degrees, that diameter is actually called an axis. So all axes are diameters, they're just special cases of diameters, but not all diameters are axes. I'm just going to explain this diagram now that I've drawn over here. If you read Apollonius' Conics, then you will find that this diagram, or something similar to it, comes up before the introduction of chords and diameters. So I'm just going to explain what the significance is and what the relationship is between these two. So here we've got our axial triangle ABC, the base circle here of our cone. Obviously I've not drawn the surface of the cone in, and what I've done in a way of speaking is I've taken a slice through the cone to produce this section DPE. So this could be any section. It looks like it's probably going to be an ellipse in this particular case, but it could be any section whatsoever. It really doesn't make any difference. In Euclid's Elements, we're told that if two planes intersect, they will intersect in a straight line. Seems fairly kind of intuitive and obvious, but it is proved in Euclid's Elements. And the intersection of that, the plane of the section with the plane of the base, is this line, this straight line here, DME. Okay. There will also be a line of intersection with the plane of the section with the plane of the axial triangle, and that's this line here, PM. We're also going to assume that the way that I've cut the section forms this line DME, so that line is actually perpendicular to the base of the axial triangle. So DME is perpendicular to the base BC of the axial triangle. And as it turns out, any line PM that is obtained in this way is a diameter. So it's shown in Heath's version of the conics, and presumably in any version that you read, that if I take a chord QQ primed that is parallel to the line DME, then it will be bisected, and it's bisected here at V, so that proves that PM is actually a diameter. So what this shows is that some diameters can be obtained in a very concrete way, so they can be realised in a very concrete way. So rather than being completely abstract things, this kind of proves that diameters can actually be constructed, that there are actually these lines that we can call diameters. They might all be obtainable in this way, but there might also be some diameters which can't be obtained quite in this way. Either way, at least we know we're talking about something. Just going back to this original diagram that I drew, I've got the last few notions and definitions really to introduce before I wrap up this video. If I take any point Q on our section, then there will be one of this series of parallel chords which is bisected by this diameter PM, which will actually pass through Q. Okay, so let's say for sake of argument that it's this Q primed, which is bisected at V by the diameter. Then the line QV is said to be drawn ordinate-wise to the diameter. And we can do this in general for any point on the section. So take any point, and if we draw a line from the diameter to that point on the section, such that that line is parallel to the chords in that family of chords, then that line is said to be drawn ordinate-wise. And Q in this particular case is called the ordinate. And once we've got the notion of an ordinate, we can talk about its abscissa. So the line QV is drawn ordinate-wise to the diameter PM, while that line segment PV, which is a line segment part of that diameter, that's said to be the abscissa. The abscissa to Q. It's also the abscissa to Q primed as well. So now we've got both of the notions, ordinate and abscissa. And what this does, what the introduction of a diameter does, it kind of introduces a kind of coordinate system into things. Now it's not a coordinate system that Apollonius uses in the same way that we might use Cartesian coordinates, but it is roughly speaking a coordinate system nonetheless, although it's not treated in exactly the same way. And you can compare the language that's used, ordinate and abscissa. Sometimes these terms get used in modern geometry. So when we've got a pair of coordinates, we've got the x abscissa, the y ordinate. They're not always referred to in that way, but sometimes they are. So the language is really quite similar, and you can see some of the similarities between PM here and maybe the x-axis. It's maybe not to be taken too literally, but nonetheless, the introduction of a diameter, it does introduce a kind of coordinate system into things. So I just want to talk a little bit now about the relationship of Apollonius's work to Euclid's work. So Apollonius presupposes Euclid's work. So even though Apollonius doesn't have a series of postulates and common notions like Euclid did, they are presupposed. Obviously, new definitions of new terms will be introduced as and when they're needed, but sometimes as you read through Apollonius, it is worth actually referring to Euclid to explain some of the results, some of the steps that are being taken in some of the proofs and the constructions that Apollonius makes in his work. You don't need to know Euclid's Elements inside out before you read Apollonius. If you've never read Euclid's Elements, you could still read Apollonius, but it might make it a little bit trickier from time to time to understand how Apollonius how he knows that he's able to do certain things, particularly involving proportions. So some of the manipulations of proportions and ratios and things like that follow straight from Euclid. It might be worth it if you are going to go through Euclid's to have, for example, book 1 is used quite extensively, book 3, book 5, and then there's other propositions that are from the other books, but it's mostly books 1, 3 and 5 I find that are going to be most useful for reading Apollonius. So I'm going to go through some of Euclid's stuff, just to give a bit of an idea what kind of things might be necessary to bear in mind. So the first one that I'm going to kick off with is, I think it's book 3, proposition 35. Can't remember exactly off the top of my head, which amounts really to effectively the intersecting chords theorem. So if you've come across that theorem before, it's effectively that one. So what Euclid says is that in a circle, you've got two chords that intersect on the interior. We're just interested in the interior intersections. Then the rectangle contained by the segments of one of the chords is equal to the rectangle contained by the segments of the other chord. So in other words, AX times XD is equal to BX times XC. And more specifically, we want to use this in the case where actually one of the chords is bisected. So I'm just going to redraw the diagram. Okay, so A, B, C, D, X. Okay, so this time we've got two chords that intersect, but one of the chords actually bisects the other. Not necessarily 90 degrees, but it bisects the other chord. Well, applying this intersecting chords theorem, we can say AX times XC is equal to dx times xb. But because the chord BD has actually been bisected, then bx is equal to xd. So I can say that this is equal to dx squared, for instance. I could say that it's equal to xb squared. But this particular form of this proposition is used quite extensively in Apollonius. The next result from Euclid that I want to mention is book 6, proposition 4, which says that two equiangular triangles have their corresponding sides in the same proportions. So what that means is, if these are my triangles, and they're equiangular, then the ratio of AB to A primed B primed is equal to the ratio of AC to A prime C primed, and that's also equal to the ratio BC to B primed C primed. So this is just similar shapes. From a modern perspective, this is a very elementary result, but it is something that's used very, very often in Apollonius's work. There is another little fairly obscure result from Euclid's book 2, proposition 5, that seems to be used often enough, at least, in Apollonius's work. So consider the line, the following, the diagram that I've drawn on the board. AB is a line that is bisected at C, so we've got AC is equal to CB, and then D is just another point on this line segment CB. Okay, well, it turns out that the rectangle contained by AD and DB plus the square on CD is equal to the square on CB. This does seem to come up quite often in Apollonius. It's one to watch out for, and it really does explain some of the steps that he's taken that seem to be quite strange from time to time, but they're entirely justified when you find the right theorem sometimes in Euclid. So finally, I just want to go through a few more principles from Euclid's Elements, really relating to manipulation of proportions and ratios. So as you can see on the board, I've written a few different rules: componendo, separando. So these are relating to different manipulations that I can make to ratios. So if we look at the first one, componendo, if I know that the ratio of A to B is equal to the ratio of C to D, then I can add in each ratio I can add the antecedent to the consequence and replace the old antecedents with the new sums. So in this case A plus B, in this case C plus D, and I'll get some new ratios, but I can say that they're equal at least, so I can maintain that equality between the ratios in this way. Separando, rather than finding the sum of the antecedents and the consequence, I find the difference. Convertendo is quite similar to separando, except it's rather than replacing the antecedents, I replace the consequence. Invertando means that I can interchange the roles of antecedent with consequence in both of the ratios to again get two new ratios, but they're going to be equal. And alternando means that I can kind of switch these two around, so the consequence of the first ratio I can interchange with the antecedent of the second ratio, and again new ratios, but they're going to be equal. This is something that's used an awful lot in Apollonius's work, the idea of a mean proportional. So if D is a mean proportional to P and Q, then D must satisfy this equality. So the ratio of P to D is equal to the ratio of D to Q, or alternatively, D squared must be equal to P times Q. And this actually follows from this last rule that I've written here. So if I know that the ratio of A to B is equal to the ratio of C to D, then I know that A multiplied by D is equal to B multiplied by C. So all of these are used quite extensively in Apollonius, and they all come straight from Euclid's Elements, particularly Book 5. So on that note, I think I've covered pretty much everything that I want to cover in this video. That last little bit has gone on for a little bit longer than I expected it to, but I think it's worth it just to make sure that all of the foundational principles are there really for somebody that wants to read Apollonius, and hopefully it'll make it a little bit easier for anybody that does want to do that. So I've covered the definitions, some of the basic definitions. I've not really gotten to the main body of the work in this video. That's going to be what I'm going to move on to in the next video that I'm going to make. But I'm going to finish there with this video. Thank you for watching. If you've got any questions about anything that I've presented in the video, please let me know. And with that, I'll look forward to seeing you in the next video.